Nice.
Uh, Thank you. So once again, thank you very much for attending uh, our event. So today we are very privileged to have a multi-awarded Filipina physicist who's going to give us a talk on quantum physics. So let me introduce myself first. My name is Bobby Corpus. I'm the president of One Quantum, and together with me is Bernardo Bueno Obra, who probably will introduce himself. Birds,
Okay,
would you like?
so yeah. Please call me Burns now, Bueno Obra. I actually it's a good occasion that I met very important friends. No, sila si ngayon si Bobby tapos si Jack whom I had a privilege to be work in the same lab from when she was undergrad to masters and up to like PhD. Uh, the my attraction to quantum computing is really on how to apply this to the area of quantum agriculture and things like that. My background is pretty much engineering and physics, but most of them has something to really work on software and hardware and design things and experiments. So I would like to thank Jackie for giving us her time, a very valuable time, in giving us her talk. Uh, and
Okay,
thank you very much. Yeah.
thank you, Birds. So let me introduce One Quantum first. One Quantum started as Quantum Computing Philippines in 2017, and this year we became part of One Quantum Global Community and as One Quantum Philippines. So our mission is very simple. Um, we want to promote quantum computing and quantum technologies in the Philippines, and we have it in our sight the future generation. So which means that as much as possible, we want to um, be able to influence the education in the Philippines so that our um, young young ones will become quantum native. And actually, we are in a very exciting time because quantum computing in the Philippines has just started its journey, and the government is very keen on having that. So, um, yeah, so now I'm going to introduce our guest speaker, and I'm going to to read her bio. So, our guest speaker is Dr. Jackie Romero. She is an expert in experimental quantum information. Her research is focused on using higher dimensional systems for exploring curious quantum physics phenomena and developing future quantum technologies. She is the group leader of the research team qudits at UQ. There's more information on her group's webpage. So Jackie was born and bred in Manila, Philippines. Hearing her high school physics teacher complain about quantum physics, she became curious and Googled quantum physics. She has been hooked ever since. She holds a BS Applied Physics magna cum laude and MS Physics degree from the University of the Philippines. She finished her PhD at the University of Glasgow in sunny Scotland, where she was a researcher for 7 years. In 2015, she moved to Brisbane to join the quantum technology group at the University of Queensland. In 2016, she took up ARC-DECRA fellowship with the same group. In 2019, she took up a Westpac Research Fellowship and formed her own qudits at UQ. Jackie is recognized for moving the shape of photons to mainstream quantum information. She has received several prestigious national and international awards, which include a L'Oreal UNESCO for Women in Science Award in 2017, one of four in Australia, the Ruby Payne Scott Medal of the Australian Institute of Physics for excellence in early career research in 2018, and a L'Oreal UNESCO for Women in Science International Rising Talent Award in 2019, one of 15 awards globally. She is currently Associate Professor and Westpac Research Fellow. She is also a Chief Investigator at the Center of Excellence in Engineered Quantum Systems. So, ladies and gentlemen, please welcome Miss Dr. Jackie Romero.
Hello, hello po. Good morning. Salamat Bobby, salamat Sir Bern, salamat po sa pagpunta sa aking talk on a Saturday morning. So I could tell mga quantum enthusiasts tayong lahat, and that's good. I must say ang aking role in quantum land is very near the hardware, if I may call it hardware. So hindi ako quantum algorithms person or yung medyo sa higher levels of the stack. I'm very close to the physical systems. I'm a physicist. So yung talk ko ngayon will be very physics based, pero sana you still also find it interesting kasi quantum physics is really, yeah, very interesting from a very foundational point of view, like your really basic view of the world. And very interesting din siya dahil sa mga applications na pwede nating
Mm.
gawin sa kanya. So as Bobby already said, I'm from the University of Queensland. Nakikita ba yung mouse ko? Nakikita yung mouse ko, Bobby?
Yes, yes.
Okay, nakikita, okay. So I'm from the University of Queensland, and also I'm part of a center of excellence in Australia that's focused on quantum technologies, engineered quantum systems. I'm a
Mm.
chief investigator there. And over the years, I've been funded by the Australian Research Council, by L'Oreal UNESCO for Women in Science Foundation, and Westpac. So Westpac actually is one of the four largest banks here in Australia. They
Mm.
invest in mga emerging technologies. So I think that would also be something that would be great to see in the Philippines for the private sector to invest in emerging technologies that not necessarily would bring
Mm.
profit the next 5 years or so, like what quantum is. Anyway,
Ah.
okay, so first I'd like to tell you where I am. So I'm in the University of Queensland, in the St. Lucia campus.
Mm.
um, it's actually a very nice campus. There's a
Yeah.
river a river
Mm.
in Brisbane, and we're in this peninsula kind of
Mm.
campus. This is the physics building. Hindi kayo mawawala. May physics nakalagay. This actually, if you look at the relief sculpture there, that's actually Schrodinger's cat, dead and alive, and the
Mm.
Tower of Pisa. Um,
Ah.
Very nice. It's a very nice campus, and we have the longest running
Yeah. Sa kanila pala
physics
'yun. Mm.
experiment in the world. It's called the pitch drop experiment. So ito, pag tiningnan mo siya, it's like a solid, hard thing, pero it's actually a fluid that's dropping very, very slowly. So I think we get one drop depende sa humidity and temperature. It could vary between, 10 to 14 years. So there's a video link actually. Pwede kang tingin ng live stream ng pitch drop experiment. It's been running since 1927. And as Bobby already said earlier, I have my own research group at UQ. So I work with postdocs Marcos and Daniel. I have an MPhil student. We have a website, quantumatibapa.org, if you want to find out more of what we do and our work. We're always looking for people to work with us. So if you're thinking of doing a master's, PhD, or kung gusto nyong, if you already have a PhD and you want to do a research fellowship, we're very happy to help you apply, and sometimes you also have positions available. So the plan for today is to tell you about qudits first and foremost. So we always hear about qubits when we read about quantum computation and quantum communication. Pero actually, bukod sa qubits, meron ding qudits, this D-level systems. And then after introducing qudits, I'll show you two experiments where we use qudits. One has a very foundational flavor. It's challenging how we view knowledge, or how we view objects. So I want to convince you that the ignorance of the whole does not imply ignorance of the parts. That's the first experiment. And the second experiment I'm going to talk about is how to describe quantum states when these quantum states are changing with time. And how it's a a very simple application of machine learning to a quantum experiment. Okay, so first I want to introduce what qudits, like why would we be interested in using qudits? So ang difference between a qudit with a D and a qubit is really just the number of levels where you encode information. For qubit, we say it's a superposition, say, of 0 and 1. So the cat that's both dead and alive. Ang qudit, you have more levels that you could encode information. So instead of superposition of just 0 and 1, you have superposition of 0, 1, 2, 3, as many as your physical system would allow. And using those higher level of encoding information, naturally, you will get a higher information capacity. You become robust to some noise kasi may natural redundancy when you use qudits. And if you think of quantum communication, it gives you more security if you use qudits. So in quantum physics, we say there is no cloning theorem, meaning if you do not know what a quantum state is, you cannot make a copy of it. So it's a no-go theorem. You cannot make a copy of a quantum system that you do not know. But the catch is if you are actually prepared to accept some failure. So say if you want to clone, pero sabihin mo, it doesn't have to work 100% of the time. Pwede kang mag-clone, and that's what's called optimal cloning. Now, optimal cloning actually has a success rate that's inversely proportional to the dimension of the system. So what it means is that optimal cloning becomes more difficult to do kapag higher dimensional systems yung ginagamit. So in that way, qudits give you added security from cloning. But aside from these benefits, there are also some things that you can only do with qudits, and I want to focus a bit on what those are. There are also things you could do only with high dimensional entanglement. So I guess you maybe would have, may talk na ba before about entanglement?
Wala pa.
Wala pa, okay, naku patay. Okay, so
Yeah.
entanglement is okay, I'll explain a little bit ang entanglement. Okay, so we when you have, so ang entanglement nagsimula talaga siya sa isang thought experiment ni Einstein noong 1940s. Kung meron kasi in quantum physics, you could have pairs of particles. So may dalawang particle and then they could be separated. It doesn't matter kung gaano sila kalayo sa isa't isa. And then when say you have in quantum physics, we usually say Alice and Bob. Si Alice and Bob yung dalawang party na merong particle. So say si Alice, she makes a measurement, and then when she does that measurement, parang we say parang si Alice Alice knows what Bob's measurement outcomes would be. It's like meron siyang seemingly information transfer, pero actually walang information transfer. It's just quantum physics. So entanglement are correlations of objects that are physically separated. Pero very different siya sa correlations na meron tayo naturally. Kasi kunwari, I have a box. So say, we play a game. There's a box. It has two balls. Alam natin na ang isang ball ay blue at ang isa ay red. Okay? So, kunwari naka-blindfold ako tsaka si Sir Burns. Naka-blindfold kami. Kuha kami ng ball, one each. And then, without looking at the ball, naka-blindfold pa rin kami. We go to separate rooms. Ako, pagbukas ko ng pagtanggal ko ng blindfold ko, nakita ko na red yung ball ko. So, at that instant, alam ko na yung ball na kay Sir Burns is a blue ball. So, merong correlation yung red ball and blue ball naming dalawa ni Sir Burns. Pero that actually is a classical correlation, di ba? Correlated yung me having a red ball and Sir Burns having a blue ball. That's correlated. Pero it's a classical correlation kasi ang balls at the very beginning, they have their property that is color, and when you separate them, they both carry that property. Ang entanglement, it's a very different kind of correlation because the objects are quantum in nature. So it's like really when somebody measures, parang dun pa lang nagkakaroon ng property na color. So, pwede kong buksan, makita ko siya na blue, pwede ko siya makita na red. So, what I get will always be random, but what I get will always be correlated to what Sir Burns gets. So, parang you have random outcomes in one party, pero it's always correlated with the other party. So, it's a type of correlation that you cannot create only with classical objects. So yung example na yon ay entanglement of two, like a qubit entanglement. Pero pwede ka rin magkaroon ng high dimensional entanglement, and that's actually very interesting, and there are things that you could do only with high dimensional entanglement. So one example actually may be of interest to you. So merong paper dati 1999, it's called How to Share a Quantum Secret. So this is the scenario, okay? You have a dealer. So tawag sa in literature usually ang tawag sa kanya ay dealer. So the dealer has a secret. So kunwari yung picture ni Einstein yung kanyang secret. Gusto niya siyang i-share sa 4 parties. And yung secret na yon parang i-break up niya into shares. So each of these will be a share. And then the idea is yung mga shares na yon pwedeng may mawala. Pwede rin na yung mga parties hindi pala sila lahat trustworthy. So yung isa hindi siya magko-cooperate to reconstruct the secret. So what this paper has shown is that even if meron kang untrusted party, even if meron kang loss, pwede pa rin ma-reconstruct yung secret using the protocol that they have here. So mabubuo pa rin yung secret kahit na only a subset of the parties can be trusted. So there are 2 important numbers here, N and K. So in this case, ang tawag dito ay a 4-3 threshold scheme kasi meron siyang 4 parties at 3 lang yung trusted parties. So what this paper has shown is that ang 3-2 threshold scheme does not exist using only qubit shares. Kailangan mo ng entangled qudits. So, doon na pumapasok yung sinasabi ko kanina, kailangan mo ng, may mga protocols you do only with high dimensional entanglement. And the good thing about using high dimensions as well is you could actually, have protocols where you don't even need many detectors. So for example here, this is also a secret sharing scheme where instead of you have 3 particles or 4 particles that you distribute, meron lang silang 1 particle that they pass to one another. And again, even if one of them could be is untrusted, mabubuo pa rin yung secret at the end. So this is quantum secret sharing with just one detector. And this is really important, especially when we start doing quantum networks in the future. Kasi mahal ang mga detectors and measurement systems. So we should make it as economical as possible. And I think qudits will help achieve that. There has been actually an experimental demonstration of this protocol recently, where they used photons, single photons. They used shape. And that's my segue to introduce my favorite system, which are photonic qudits based on shape. So ang photons, they are nothing but particles of light. At alam natin ang light, marami siyang property. Um, Merong color, which is associated with the wavelength. Meron ding path, which is kung kunwari meron kang laser, pwede mo siyang i-divide into different paths. Pwedeng dumaan yung light dito, dito, or dito. Meron din tinatawag na time bin. So time bin is like when you have a detector, which bin did the photon arrive. So pwede ka rin mag-encode ng information dun sa time of arrival na yun. What I've been using mostly in my research is what I call shape, the transverse mode of photons. So if you notice here, the intensity of this light is not your usual laser beam. So laser beam, di ba meron siyang bright spot in the middle. But actually, we can shape light into anything we like. Pinaka-popular siguro, especially nung mga early 2000s, is what they call twisted light beams like this. And that's because when you look at the wave fronts, it has a twist and they look like donuts. Yung intensity niya is like a donut. And it's been one of the most important experiments in the field was actually when the entanglement of this twisted light was established. So, importante na napakita yung entanglement because when people think of quantum physics, it's really what is the quantum phenomenon, yung entanglement. So those twisted beams, it has a nice physical property kasi maa-associate mo yung shape niya into what's called orbital angular momentum. And it has a very nice analogy with the orbital angular momentum that you have in an actual harmonic oscillator, yung mga sa spins, yung mga other physical systems. So, madali siya maganda yung correspondence niya. So yeah, people really like that. So this one was an experiment in 2001 where they showed the entanglement of OAM. So yung pag sinasabi kong entanglement na may dalawang particles and they have quantum correlations, it really sounds like magic, no? Pero actually, you can do that in an experiment. So this is the experiment back in 2001. You have a UV laser. So UV, I think they used I'm not sure what wavelength, pero very high energy photon. In my experiments, I use either 355 nanometers or 405 nanometers. So you could buy UV lasers, and then you get a nonlinear crystal. So nonlinear crystal, it has this capability that if you bombard it with a high energy photon, there's a probability that that photon will split into two photons of a lower wavelength. So in this case, meron tayong UV. After ng crystal, magkakaroon ka ng dalawang infrared photons. And these infrared photons have many properties that are entangled. But we focus on the OAM. So yung OAM, yung kanyang, I like to call it like the shape. You could measure it with a hologram. It's really a hologram. Like in this experiment, actually, nag-develop sila ng hologram, as in a fixed hologram. Yung gumagamit ka ng chemicals to make that sheet. Tapos ilalagay nila dun sa experiment nila. And then there's a single mode fiber, like very similar to the fiber that carries our internet, except that in that fiber, it only supports one shape. It only supports one mode of light. Tas yung fiber na yon connected siya sa single photon detector, which you then process with some electronics para makuha mo yung data sa iyong experiment. So this one would be, uh, uh, this one is the typical setup, how you, so tingnan muna natin, how do you give light a particular shape in the first place? Before we even talk about detecting in a single photon what that shape is, let's talk about how we give beams shape. So if you have a laser beam, it would usually be a Gaussian spot like this. You have a bright spot. Then you get one of these holograms. You make one of those holograms. So as you could observe here, what happens is after this hologram, you have two directions. After nitong grating, may two directions na yung light beam, and the beam that's in the direction of the first order has the particular shape that you want, that you design this hologram to make. So this is how you generate. You have a Gaussian beam, a bright spot, then you have the hologram, and then in the first order of this hologram, you get this nice donut-shaped beam. Now, optics is really nice because optics works backward. So yung genius nung paper na yun nung 2001 is that they realized that this setup could be turned into a detection system. So, sabi ko kanina, di ba, yung fiber, it accepts only one mode. It accepts only a bright spot like this. So, kung yung fiber na yon, merong bright spot na nakouple into that fiber, ibig sabihin, merong bright spot, may fundamental mode that coupled into it. So, saan siya manggagaling? Manggagaling lang siya sa light that was transformed back into a Gaussian mode. So it's like, kunwari, meron ako ditong hologram which had the opposite donutness of this beam here. So parang magka-cancel sila. So magiging siya dito, Gaussian mode siya. And that's the only shape that would couple to this fiber here. So pag pinalitan mo to, ibang shape naman yung mame-measure mo. So ganon. It's a really very elegant, simple idea. So what I've done which was taken up widely, is that instead of using those fixed holograms, sabi ko kanina, di ba, dinidevelop mo siya for every shape that you want to measure, you make something like this. So what we did in my group, where I did my PhD, we use programmable elements. So we use what's called a spatial light modulator, so that this measurement can be made more versatile. And it's really an SLM is really like an LCD. You have liquid crystals on top of a silicon plate, and then when you vary the voltage, the liquid crystals orient themselves in some way. So the index of refraction, the phase delay changes, kasi kung titingnan mo dito, mas konti yung physical distance na naka-delay dun sa light compared dito nung naka-diagonal sila, di ba? So, meron kang kakayahan na ngayon na i-shape yung reflected beam with these SLMs. And it's very nice because it's programmable. And we've taken this, so this technology still exists. I think we're getting better and better. In my experiments, we just use one bounce of an SLM, but these days you could do more than one reflection, and you could do more interesting things. Like this one, for example, if you think of your multiplexer, demultiplexer, di ba? Very, common siya sa classical communication. In quantum, actually, we're still developing those things. And this is one example of a multiplexer, demultiplexer for photon shape, using 7 bounces of an SLM. And it's yung being programmable is really important because, as I've said, there are so many shapes that you could use. These are just some examples. So they're all solutions to the wave equation, to the paraxial wave equation. It really doesn't matter what family you use, for as long as you have an orthonormal set of shapes, you could use that to encode information. If you want to know more about entanglement, qudits, I actually wrote a high level article in Optics and Photonics News. Like, I could send you a PDF of that, or kung member kayo ng OS ng Optica, it's in their January 2022 issue. And there are some really nice graphics there explaining yung mga quantum phenomena that doesn't have counterpart in classical physics, for example, entanglement and complementarity. So you might find that interesting kasi yun talaga yung basis ng power ng quantum physics. Okay, so I hope medyo kilala na natin yung qudits, so I could describe two experiments for you. So as I said, one is really, we did it because it's very curious. It started from a paper which I read in 2011. And the title was, Does Ignorance of the Whole Imply Ignorance of the Parts? It caught my attention kasi meron siyang cartoon. May cartoon yung Physical Review Letters article. So PRL is it's a top journal in physics. Einstein and other famous people published there. So it's, when I saw a cartoon, that's really cute, and turns out to be interesting. And I did this work with a PhD student, Michael, Sally, who is a philosopher, physicist, and medical doctor, and Andrew, who was my boss dati nung lumipat ako ng UQ. And this was published in this article here in PRL in 2020. It was on the cover. And there is also a popular article in Uric Alert. So this gives like a summary of this paper here. Okay, so first, I have to we have to talk about whole and parts. And in quantum physics, na maraming beses ko na nasabi, in quantum physics, when we think about whole, usually the idea that we have is an entangled pair. So yung particles that are separated, there's like one description of these two particles, that's the whole. And then the parts would be each subsystem, like each particle is a part of this whole. But actually, when we were doing this experiment, we realized you could do away with entanglement. We actually just use a dit string. So when I say dit string, it has a string y0 y1, and y0 and y1 could be any of the letters. So it's really just a string. And the physical intuition that's central is, as D increases, of course, randomness increases. So paano ka ba nagde-test ng randomness? You do an experiment over and over, or you take a test over and over. So that's what we did in our experiment. Like you measure things for many photons so that you could characterize randomness. So wholes and parts, and then next I have to tell you, how do I measure ignorance? Kung meron sa inyong mga probability or statistics, you may be familiar with this notation. So this is a probability of guessing y given, so it's a conditional probability of guessing y given there is an encoding E. And the mean entropy is just the negative logarithm of this probability. Sorry, it's just the negative logarithm of this probability. So naturally, when mean entropy is large, the guessing probability is small. So mean entropy is a good measurement then of ignorance kasi pag malaki siya, hindi mo mahuhulaan yung y. And in that PRL paper, they had a theorem which reads something like this. Hindi ko na siya babasahin. I'll just give the intuition. Um, I read it as, so this right-hand side, so this left-hand side is the ignorance of a part. So meron kang part of your system, it associated ignorance. And what this theorem says is that the ignorance of a part should at least be half of the ignorance of the whole. And it makes sense, right? If I say, for example, I don't know, if I say, if for example I have a two-page book and I don't know one, like if I say I don't know, yeah, okay, let me let me rephrase it. Okay. So it's really just a statement of, if you have ignorance of something, there must be a part in that something that you do not know of. Meron kang mapipinpoint na hindi mo alam kapag you're ignorant of something. And that's what that theory paper was trying to say. So they phrase it actually in terms of an exam. So in that paper, they were describing a student who would sit a test, and there's a teacher, so yung cartoon ng owl na teacher, and this teacher's job is to find where the ignorance of this student is. Given na yung student, meron siyang cheat sheet, so yung physical encoding na tinatawag natin na E. So yung theorem na to, sinasabi lang niya, the teacher could always point to the part that the student doesn't know. There's always this random variable that exists classically. So meaning, there is always a test that would reveal which character in the dit string the student is ignorant of. So that's what this theorem says. So in our experiment, we set it up in terms of a task. So the teacher has a task to find what that pointer is, to find where the ignorance of the student lies. So this is the theorem in terms of probability. Kung natatandaan natin kanina, meron tayong dit string. So it could come from set y0 and y1. There will be, so yung small y would be like each instance of that string. So y0, y1. There are d possibilities for each of these characters. There's a cheat sheet of the student. And then merong question. So yung question, I denote it by M kasi in our experiment, it's really a measurement. So pwedeng mali, pwedeng tama yung sagot ng student. Okay, so the probability of guessing given an encoding is, we denote it by this one. So probability of guessing part C of Y, given that there is an encoding E, and the teacher asked to the student to name part C. Okay, so the theorem in terms of this probability reads something like this. This probability will be bounded by 1 over square root of D, meaning you cannot do better than 1 over square root of D. And we can verify that with a classical strategy. So for example, ano ba yung optimal na classical strategy for this student? It would be to encode one part of the string. So say palagi lang niyang i-encode, palagi lang sa cheat sheet niya is y1. Okay? So every time the teacher asks a character from, y1, palaging tama yung sagot ng student. Pero kapag if the teacher asks what y0 is, then huhulaan ng student. So yung probability of guessing niya will just be 1 over d. So what happens here is you have the best guessing probability, which is kapag yung y1 yung tatanungin ng teacher, and a worst guessing probability, you just guess at random. And this is all very intuitive, right? Paano mo ba na malalaman na hindi alam ng student? Titingnan mo ano yung hinuhulaan lang niya, 'di ba? So it's all very just to formalize that very I guess common intuition na malalaman mo na hindi alam ng student kasi nag-guess lang siya randomly dun sa part na isa na hindi niya nasulat doon sa kanyang cheat sheet. So in this case, the guessing probability is indeed bounded by 1 over square root of d. 1 over d is less than 1 over square root of d. Now, what if yung cheat sheet ng student is allowed to be a quantum cheat sheet? So this would be, I don't even have a classical analogy for it. I don't think there is. It's just really, oh sorry. Nasaan na yung aking slides? Nakikita niyo pa yung slide ko, Sir Burns?
Yes, we can still see your slides.
Para lang
Ah?
nag-pixelize. Nag-pixelize ng...
Okay. Ayan, okay na?
Yeah.
Okay, sorry. Okay. So this one is this is a quantum cheat sheet. You write this is the equation for your quantum cheat sheet. It's what I call a qudit encoding for this 2-dit string. X and Z, they are just matrices. This is a vector. It's just something that we could write and we could prepare in an experiment. And when you do that, I'll show you, you could actually score higher in that test. So experimentally, of course, walang owl, walang student, it's all very physics-y experiment. So we have the student prepares a cheat sheet using a first spatial light modulator. So that's my physical encoding E. And the teacher is another spatial light modulator plus your single mode fiber here. So this is like interrogating the system that this student is sending. So this is my encoding. This is the measurement. And what's nice about this, yung paggamit ng SLM and the qudit encoding, is that you could really just program anything. You could program any state like this into an SLM. So for example, ito ay ito yung mga 2 qudit encoding of these strings here. So if you look at the intensity of the beam, ito yung makikita mo sa camera. So that's a 2 qudit encoding of these strings, of this string here. And then ito yung color, it's just the corresponds to a phase. Like it's not important. It's just that these different intensities have different phase, each pixel. And we could do this for many dimensions. So ito ano lang to, tatlo lang yung pwedeng i-take na values nung mga dits na to, pero you could actually do it up to 11 dimensions. In our experiment, we did it up to 14 or 15, I think. And the probabilities are standard quantum quantities. It really is, ang maganda sa kanya, yung nakikita mo na probabilities, all the traces that you see in a textbook, matatranslate mo siya into values that you could get from the experiment. So in this case, O and N are just count rates that we get from our detectors. So it's really it's all very straight. It's all very easily mappable to the experiment. Kaya it's a very powerful system. So, quantum strategy. So, say, ito yung cheat sheet ng student. That's the different encodings for the different strings. Once you calculate the probability, you'll find this now will be the probability. So, as you could see, regardless of what the teacher asks, whether the teacher asks for the first or the second character, the probability of guessing is the same. And more importantly, neither of these parts are being guessed at random. So if you recall the theorem in terms of the probability, diba, it should be bounded by 1 over square root of d. In this case, this inequality doesn't hold anymore. So ibig sabihin that theorem does not hold when you have a quantum encoding. And what it also means is that if you have a quantum encoding of that system, the teacher will not be able to pinpoint which part the student would be ignorant of, kasi as you could see, wala ditong randomly guessed na part. And I think that's cool. So what you could also do is you could score higher with a quantum encoding. So kung matatandaan natin yung optimal strategy kanina, meron kang yeah, you always guess one part correctly, but you guess another part randomly. So kung ika-calculate natin yung score, assuming na half the time the teacher asks for part 1, yeah, for Y1, and half the time the teacher asks for Y0. Okay? So yung average score mo would be 75%. Pero using a quantum strategy, if you calculate the score, you get around 85%. And as you go higher, you get bigger difference. I think yeah, 6 or 7, I think, is the optimum difference between the two. I mean, that's also interesting that there is an optimum. Okay. So, I think isi-skip ko na to. This is just to say na kapag classical cheat sheet, you really actually get a correlation. So madidetect mo kung anong part yung hindi alam ng student. Pero when you do a quantum encoding, this probability is uniform. Okay. Okay. So I hope with that first part, I convinced you. Sandali lang po. Mayroon akong anak na kumanap. Sandali. Yes. Okay. So, yeah, so the student can get a higher score and the teacher cannot point to the part that the student is ignorant of kasi pareho yung probabilities na if you use a quantum encoding. And this is just a plot in our paper. Kung interested kayo, pinakita namin siya up to 14 dimensions. And pinakita rin namin siya even if meron kang leakage in information. So it's robust to that kind. That kind of leakage. Okay. So this one siguro hindi ko na I will not explain this. It's just for, I guess, if kung merong interested sa experiments, this is a question I often get asked, why I don't use yung nonlinear crystals na pinakita ko kanina, yung how yung nagpo-produce ng single photons. And I think it really is not necessary. And I think especially kung when I was in UP pa, and you read this, there are many quantum papers that use this, UV plus crystal plus, detectors. They look very resource intensive. So I had the impression na yung quantum, pwede mo lang siyang gawin kapag meron kang lahat ng yon. Pero actually, if you notice yung experiment na pinakita ko, it was a laser. It was just a laser na inattenuate namin para medyo mas mahina yung intensity niya. So it was a very cheap system. And it's something that I hope people in the field emphasize more, that there are experiments that you could do even with the laser and show quantum stuff with. I think more people, especially in the developing world, would join the quantum enterprise kung may mga ganon na pwede nilang gawin. Okay, so yan, hindi ko na yan i-discuss. Hindi ko na rin yan i-discuss unless you could ask me about it. It's all about, philosophy and quantum physics, which is also, very interesting. Pero I find a lot of, there's a lot of baggage there too. Okay, so yung second experiment is about, I say finding knowledge because in quantum physics, for us, knowledge is really embodied in the quantum state. If you know what the quantum state is, then you know everything that there is to know. And in this experiment, we did something really cool, I thought, because we could do quantum state tracking, meaning even if the quantum state is changing, and even if there is noise in the environment. If there's even if your experiment is noisy, you could find what the quantum state is. So we have the manuscript on archive. You could look it up here. It's work I did with Marcus Akram and Marco, the collaborators. So quantum state. Finding the quantum state is often called quantum state tomography or quantum state estimation. I think in the literature they are used almost synonymously. And quantum state tomography is really about the question, what's the best quantum mechanical description of a physical system? It doesn't matter what the physical system is. It could be a row of ions. It could be the photons coming from a crystal. It could be light coming from a laser. It's any physical system. So the assumption is that there is a true physical state, which I denote by rho, and then that physical system is outputting some data. So this state is giving us some data from our experiment, and then from measurements in the experiment we apply some algorithm. Usually it's maximum likelihood estimation, which is order d to the fourth algorithm, para makuha natin yung rho, yung density, yung quantum state. Now, the problem with this, we do it routinely, but it's actually computationally expensive and it's also sensitive to noise, because it uses probabilities. And it's actually even more challenging to do state tomography for qudits because the parameter space grows as d to the 2n. So if you have n qudits, you have d to the 2n minus 1 parameters to estimate. And more parameters to estimate means that you need more copies just to keep your uncertainty at the same level. Kailangan mo ng mas maraming copies of the physical system. And the probability of getting at least one negative eigenvalue or a zero eigenvalue becomes higher as well. So in quantum, ayaw natin ng negative eigenvalue at saka zero eigenvalue kasi ibig sabihin hindi siya physical system. It's not it's not a quantum description kung meron kang negative or zero eigenvalue. So yun. Yeah, so what if now, so additional to, that you have a high dimensional system, you want to find the quantum state. Now, what if the quantum states change as well? And this is a physically meaningful, question kasi pwedeng ang quantum state mo, magbabago siya intentionally. Say you have a quantum state that undergoes some Hamiltonian or some process. It will go through some process. So naturally, it will become another quantum state at another time. So you might want to characterize that. Or, a quantum state could change unintentionally as well. So say you think you're going to send your quantum state in a very nice, clean channel like that. And it turns out you are in, I don't know, planet Arrakis with the sandworms, right? So na bago na yung quantum state. How do you know what that quantum state is? So we've thought about this. So meron kang quantum state in a black box. So, for example, in one experiment, meron silang polarization of light lang. So, polarization meaning you have meron kang alam yung Polaroid sunglasses, di ba? Yung may polarizer. It actually gives you light that's only vibrating on one plane. So, polarization is the plane at which that light, that the electromagnetic wave is vibrating. So, we call that polarization. Characterize mo an angle theta. So we could encode information in polarization. So tawagin natin yon na theta. And this experiment here actually just showed that you could, even if that theta is drifting, you could apply some state estimation techniques, adaptive state estimation techniques, such that you could follow the drift. So in this case, they were changing their measurements based on the data that they were getting. So they were like changing their experiment based on the results of the experiment. So in some way, very, parang feedback, ganon. So in our experiment, we used another way to track quantum states. We call it matrix exponentiated gradient tomography. yeah, related to the gradient techniques that we have in yeah, machine learning. And the good thing about it is it's online, meaning you know the state in real time. It runs fast. So if you look at the comparison between MEG, maximum likelihood, and least squares, MEG is faster. um, and it's robust to noise, as we'll show, and it has a convergence proof. So convergence proof, like when the theorists would write their proofs, there are some values of the learning rate for the MEG method that they show that it would always converge to the true quantum state. So I'll describe MEG very briefly. So a MEG is, more details are in this paper here. So ang MEG is just an algorithm where the update rule is this. You have the estimate is calculated from this equation here, where we introduce a loss function. So loss function is just the difference really between what you expect and what the experiment data is. So you could, based on an estimate, you could calculate the expected outcomes of the experiment. That's what this quantity is. And then your experiment will spit out numbers y. And then based on the difference, you update MEG. Um, so that loss function there. And then there is a parameter, eta, which is just some kind of weight given to new information. So paulit-ulit mong ginagawa yung algorithm. So you have many copies of the quantum state. And then it just, you could tune eta to whatever you like, to whatever works best for the experiment. So in our experiment, it's actually the same setup that you've seen earlier. We use an SLM for preparing. So in this case, we were preparing qudit states. So these were the different intensities and phase. So this is our basis modes. And then we tested the MEG algorithm for when we encode only a stationary quantum state, meaning hindi namin iniiba yung quantum state. It's just always like that, same copy every time, or if the state was evolving. So depending on what this sigma, so this is like an evolving state, we have some rate of change, and we have sigma matrices, which could either be a sigma z, so like a z matrix, or just a random qubit matrix. So yeah, I think that's not important. So the results are this. So yung y-axis what we call infidelity. So infidelity is just 1 minus fidelity. So when you have two things you're trying to compare, di ba? Fidelity 1 means magkamukha silang dalawa. Kapag merong difference, magiging 90%, 95%. So ganun yung fidelity. So in our experiment, dahil we're plotting 1 minus infidelity. 1 minus fidelity. So that's infidelity. And as you could see here, we're getting like 0.05. We're getting 5% infidelities, regardless of what the state is, whether it's stationary or evolving. And what's nice about MEG is that even if there is high noise, so kunwari, dito 1 million photons yung ginagamit mo sa experiment, paano kapag mas konti na lang? So, mas malaki yung noise compared to the signal photons. And still, we show that we could achieve 5% infidelity, regardless of the quantum measurements that we are doing. So yeah, it works. So this is just a table of the MEG performance. I think yung pinaka-importante dito to take home is that MEG really doesn't need a lot of iterations. So for example here, what I'm showing is after 4 iterations with a million photon signal count, MEG would find the quantum state after 4 iterations. Kung mas konti yung photons, mas matagal, 13 iterations. So it's a very efficient way of finding the quantum state. And the quantum states is, of course, you could use that for predicting what the outcomes of your measurement would be. So this is just a plot of what the probabilities that you'd get if you were to measure 0 or 1 or 2. So we just show that aside from getting the quantum state, we could actually predict the outcomes of of experiments. And the last thing we did actually is quite funny. We just added a light bulb near the our photo detector. So nilunod namin sa photons yung detector namin to get more noise. And we were tuning that noise by really moving the bulb around, no, changing the angle kung saan siya nakapoint. Ganun siya ka-sophisticated. And even then, we show that even if you have that very high noise source, with 100 photons, MEG would still converge to 5% infidelity or lower actually kung tatagalan mo pa yung iterations. So we show that even with very high noise, we could estimate the quantum state. Okay, so I hope at least some of that was interesting. I mean, you could ask me questions in the Q&A. But what I hope you're able to take home today is that qudits and high dimensional entanglement are really important, especially as we begin to scale up our quantum computation and quantum communication efforts. I hope I convince you that the ignorance of the whole does not imply ignorance of the parts. You could hide ignorance if you use quantum physics. And lastly, I showed you a very basic gradient inspired technique to find the quantum state in real time, even in the presence of noise. Okay, I think that's it. Magsa-stop sharing na ako, no? Tama?
Yeah.
Para
So,
makita kita.
so
Okay.
Burns is going to facilitate the Q&A.
Yeah.
Burns?
Okay, sorry. Parang madaming physics. Okay.
Burns?
So
Prepared?
yeah, hello. So how do I exactly do this? We use the same platform, or do we move to?
No, it's already in the comments.
Okay, yeah, right now. So
Okay. So
I
I
think
look at the
my first
comments.
question. I like to ask the first question.
Yes.
Yes.
Yeah, sure. Because I'm very happy to see again diagrams of optical diagrams, and I really like those, and I first is I really admire your work. It's really very the sophistication is brought down to an optical experiment. No, most of
Yes.
the quantum things,
Yes.
most of the
Yes.
quantum,
Exactly.
yeah, this is really the brilliance, I think, because when you try to go Google quantum, all you see is really very difficult stuff. No, like that's why I keep asking myself, how can I possibly demonstrate superposition on an optical bench? I think I asked you that one before. So is there really a way to demonstrate superposition and optical? Now I've seen it. Even machine learning. I'm doing machine learning, but really for plantation work. I have all those agronomical variables, and I
Mm.
run it, and I
Uh-huh.
get all these models. And one of the things that interests me is the quantum part, is the how to actually convert a problem to a quantum mechanical equivalent. So I've seen
Mm.
this in your QST, your quantum state
Tomography.
tomography, and
Mm.
I think that's
Mm.
this. I'm actually very happy to see that it's actually there. So ayun. So let's give the others a chance, no? I can always write Jackie anyway.
Yes.
So okay. Yes. Open. The
Mahina.
questions are open.
Okay.
Uh, okay.
Yun, nakita
So
ko yung comment.
anyone. May comments. Let's see comments. Okay. Uh, there. Let's
Ah,
begin with
Bobby's
with Bobby's question.
Okay, what's the implication for this in cryptography? Very good question, Bobby. So yung pinakita ko na theorem, yung mean entropy splitting theorem, yung ang ignorance of the part should be bounded by at least half of the ignorance of the whole. It's actually a theorem that quantum cryptography practitioners, yung mga nagpo-prove ng security of a protocol, okay,
Mm,
ginagamit nila yung theorem na yon. to
I
prove
see.
security. So ngayon with that theory paper and now with the experiment, what it's telling us is that hindi mo pwedeng gamitin yung theorem na yon to prove security kung meron kang capability to encode in a quantum system. Kasi yung yung encoding, yung cheat sheet ng student, you could think of it as a system of an eavesdropper. 'Di ba? So
Yeah. Tama.
kung yung eavesdropper meron siyang access to a quantum system, kung meron siyang cheat sheet na pwede maging quantum, hindi mo pwedeng gamitin yung mean entropy splitting inequality.
Okay.
So so yun. So yun yung message, do not use that inequality in proving kung yung eavesdropper meron
That's
siyang access to a quantum system.
mm,
Okay.
may cheat sheet siya. Okay.
Oo, kung meron
Does
siyang
that answer yeah, does
Yeah.
that answer your question, Bobby? Okay,
Yes.
let's proceed to the next, no? Asher, our student, no? Si Asher is a young student in PUP in Zambales. So,
NMR.
Asher Manangan, no? Yes.
So is there a way to produce entangled qudits and qudits by using NMR? So actually may mga NMR quantum computers eh. Hindi ako
Okay.
masyadong familiar sa kanilang how they work, pero galing sila sa nuclear spins nung nasa yun nung unsum. So ang difference kasi ng quantum NMR sa systems like mine, so I could actually give you a photon with a particular quantum state. The way I understand NMR, unsum siya palagi, parang marami siyang like yung addressability niya. So you meaning I get one spin, I play with that. Hindi siya gano'n na system. Parang palagi siyang property of a whole,
Oh,
something like that. So
Mm,
I think you could do qubits and qudits there kasi spins yun eh, so maraming levels
mm,
din ng spin. Pero yung addressability niya, meaning I pick one of those, hindi gano'n yung NMR. That's what I
okay.
think, yeah. So
Um,
actually parang, ang alam ko yung signal to noise ratio ng NMR, quantum computer,
mm,
a bit of a problem.
that's real.
Oo,
That's probably it.
oo.
So the same person asked, do you know some resources you can recommend? I think Doc Jackie could send us links, no, to our paper and also some of the where to look, no, or where to look
Oo,
like
yeah. I
links.
could
Yeah.
I could
Mm,
i-forward, i-email ko sa inyo yung PDF nung aking mga paper. Yung
mm.
isa ano pa, nire-review pa, yung tomography ay nire-review pa. Pero I hope na actually very low level machine learning nga yun, 'di ba? Parang
Yeah,
grade
it's really to
gradient
the
lang gradient lang siya na
no, but it's amazing, because it's just for me, it's just really just Python code, but really to bring it down to like a computing machine, really like an optics, it's really amazing.
hmm,
So let's ask
ah, ano ba?
Citius, something. Yeah.
How can
So,
this technology be used in designing AI chips? Interesting. Okay. So, AI. So, siguro dahil mga practitioners kayo, no, alam niyo na ang AI very energy expensive siya.
yes.
Very energy expensive siya. The way that we have designed chips, yung von Neumann architecture is not made for machine learning. So,
Uh, uh,
meron actually ng mga gumagawa ng mga architectures na tawag do'n neuromorphic computing na
yes.
'di ba,
Mm,
yung neuromorphic
yeah.
is one effort para i-address yung
Mm,
pagka-energy expensive. Pero meron din mga companies ngayon, if you look up, ang pangalan niya ata Light on IO, it's a French company I think, Light on
mm,
IO. Kasi ang maganda sa optics, it could, as Zithius here says, ang optics, very easy ang matrix multiplication. Like
yeah.
if you think
Mm,
of yung dalawa kong
mm,
SLM sa experiment ko, yung dalawang electric field na yon, it's a matrix multiplication, 'di ba?
Yeah. Yes.
Bra and ket mo sa quantum, bra and ket, it's a bra and ket operation na very, very easy to do optically.
Mm.
So yung light
Like.
on ayo, alam ko meron silang mga products para padaliin yung matrix multiplication. Actually, they are selling these now. Ang mga optical accelerators for AI. Dumadami na yung
Mm.
companies na ganun. So I think ang leading in the world would be yun, yung Light on IO. Tsaka meron ding MIT company, Dirk England. Makaka-type ba ako sa chat?
I think so. Yeah.
Yeah, type sa chat. Okay. Yan. I mean, these are the people to look up. Dirk England, MIT. I think yan ay si Sylvain Gigan in France. Well, I could send you links if you're interested. Ano siya?
Perfect.
Yeah. So yun, meron ng mga chips, meron ng optical chips that people are
Mm.
selling para pabilisin ang mga matrix-based operations.
Galing.
Nice.
Galing. Beautiful. So
Um,
si
what
Bobby
is
has
the state of quantum computing in Australia? Haha, interesting.
si-
Okay, so ano muna ang state ng quantum computing in the world? Um, in in the world, pinakamaraming attention ngayon yung mga superconducting platform, yung
okay.
and
IBM.
Google,
Google. Yeah.
IBM and Google. Um, in Australia, wala kaming nagfo-focus on superconducting platform.
Ah,
I
okay.
actually think it's a strategically din kasi
Mm.
mahirap
Mm.
makipag-compete sa Google and IBM. They're
Mm.
very
Yeah.
resourced. So yung superconducting, meron din ngayon promising yung mga trapped ion computers, quantum
Oh,
computer. Yung
trap
mga
ions.
trapped ions, so leading in the world yan, Austria, UK, US. They have, so because we can now trap ions in a lattice. So, and it's really a clean system siya kasi naturally siyang
Mm.
magbe-behave as a quantum system dahil, as in yung textbook quantum system mo yung mga ions. Tapos, yung mga gates niya, kinokontrol mo using lasers. So yeah, I
Mm.
think, so worldwide, I would say, superconducting at saka ions yung pinaka-most attention. Pero ang photonic quantum systems are also around. Yeah, so photonic, yung pinakita ko kanina na based on light path.
Mm.
Merong company ngayon, ang pangalan niya Psi Quantum. And they're getting, hundreds millions of dollars investment para sa kanilang quantum computer. Pero wala pa silang product available. So yeah, we just
Ah.
have to wait. In Australia, ang kanilang bet ay sa semiconductor. So
Okay.
in a semiconductor, you could implant ions. I think phosphorus yung ini-implant nila. Tapos
Mm.
gamit nila na qubits. I'm not sure what exactly sa phosphorus. Pero ang gusto kasi nila dito ay it would be consistent with current semiconductor manufacturing capability.
Yeah. Mm.
Tapos dahil you are implanting the ions, pwede mo siyang ilagay anywhere you like. Hindi
That's good.
kagaya nung mga iba na, I mean, you might also have heard yung mga nitrogen vacancy in diamond or other solid state systems. Ano sila, mas less yung control mo sa kanila. So yeah, so in Australia, it's semiconductor ion implanted semiconductor yung pinakamalaki ang investment sa quantum computing.
I remember in San Carlos, when I joined San Carlos like years back, uh, si John Lee Wag was MS Physics actually built a cooling laser cooling facility and showed me a trap. But the thing is that it was never maintained. But San Carlos did it, and they were able to build a that system. But we never really
Hmm.
thought that it's gonna be after so many years it can be like applied, no, right now on the
Oh, no,
on uh
exactly, laser cooling. So, yung
yeah,
mga trapped
yes,
ions mo,
yes,
marami kang lasers, like I think they
yes,
do from 6 different directions para
yes,
ma-cool down mo yung mga
yes,
sideband vibration. Yeah, so
mm,
that's the workhorse
yeah,
for ions.
yeah, that's very good. Also, I kind of remember the you're testing it for like how rugged is the setup by moving a lamp or something,
Ano lang
diba?
yun, artificial introduction of noise.
Oh, because I dealt with a lot of spectroscopy and in the plantation, and one of the things that is a problem is, for example, like you know uh, when we get the pineapples out of the farm and we brought it to cannery, some people we judge them at the color of of the shell. So when they are brought to the cannery and harvested from the plant to cannery, we have some correlation of what the ripeness is. Problema when people look at the shell color in the cannery, they are riper than what we thought here sa sa farm. So I kept thinking na why is it like pagdating ng fruits doon sa cannery na hapon na, they think that's really ripe. So sabi ko, siguro malabo lang talagang ilaw, no? Because we get them like tanghali, no? And then we brought it travels all the way to Bugo, like in hours or maybe days, no? Kaya lang, I kind of remember that the basic fundamental thing is that our illumination in the plantation is the sun. It's the sun. We don't
Yeah,
have
yeah.
any power. When we bring it to the cannery, their illumination is fluorescent bulbs,
Mm.
halogen. Halide, mercury halide. And when I took the spectra of hydrogen halide and all of this light, you have spikes on the spectra.
Mm.
So I was thinking that what if you actually introduce mercury halide with or fluorescent instead of CD just incandescent to test
Okay.
it because
So
it's going to create a spike.
yeah,
It's
no, so what I didn't mention is that in front of our detectors, naglalagay kami ng bandpass filter. So yung bandpass filter namin, it's 10
yeah,
nanometer wide, around 810. Hindi ko alam kung ano yung spectrum ng
it's probably
mercury.
flat. Yeah,
Or
it's
baka wala.
because
Yeah.
if you're using halogen, it's gonna be flat. It's really flat. So
Yeah.
pero yung halide is really and mercury, it really it really destroys your sense of
Yeah.
color.
Mm.
So well anyway,
May
si Tius
tanong.
kasi yeah, ito
Ah,
baka gusto mo
Hindi.
mag-migrate sa Australia nito.
So I think actually ngayon, marami ng companies na nagbibigay actually ng some kind of training in quantum dahil there's a lot of interest at the moment. So I think even if you don't have a degree, kung yung company mo ay interested in quantum, you could get training from them. Um, kung gusto mo ng formal na degree, marami na ngayon na like for example, in University of Queensland, meron kaming masters in quantum technology where we are taking graduates of courses na you could have any background. Kasi ang
Oh.
quantum technology hindi lang naman physics yung kailangan niya.
Oo,
Kailangan
engineering din.
maraming,
Yeah.
maraming,
Yes.
maraming disciplines. So may
Mm.
mga master's program that you can do na mga 1.5 to 2 years in duration. Tapos, meron kang, so that would give you exposure to yung mga iba-iba na mga kailangan. I mean, in the end, actually, to be honest, depende sa kung saan mo gustong pumunta. It's a lot of linear algebra.
Ah,
And kung gagawa ka ng experiments, actually, engineering is actually very good
yeah.
back. And a lot of companies actually now, kunwari ang IBM Quantum of course may Qiskit,
Yeah.
ang Google may Circ, I mean sometimes I see yung Black Opal, yung sa Quantum Q Control, marami ng mga ano ngayon, mga like parang
Yeah.
self-paced na mga
Mm.
training that you could do.
Tsaka
Tas
free.
yeah, and they are also free.
Yeah.
Yeah, I mean, so when you say quantum engineer as in to work in a quantum startup company, ganun ba? O yeah,
Yeah, I
ano
guess this is a
yeah.
professional work or something.
Yeah,
So I think that's all the question there is. But we can always write Professor Jackie here, no? If she can be, she can. Maybe you can. If it's all right to write you, by the
no,
way,
no, no, it's
and
okay.
ask.
I am very
Uh,
Googleable. Pwede
yeah.
niyo akong
So
email sa aking email address.
uh,
Ah, okay. Ah, yeah. Hindi ako maka-type dun sa comment section. So, pakilipat na lang yung aking
Uh,
mm.
email address.
so
Yes.
so guys, now if you haven't seen a real Wonder Woman, we have one here. So so okay. Uh, Naalala ko pa yung poster nung quantum optics may poster ginawa mo dati na you explain the all the it's a quantum optical setup dati nung
Mm.
dati noon. Oh. Susulat ako sa iyo ha, Doc Doc.
Yes, yes. So, walang problema.
So
Email.
Bobby, do you have something? Our
yeah,
president.
thank you so much, Jack. It's so nice to see you again.
Yes, nice to see you again. And you should tell me more. So, actually, sige, maybe when the rest go. Anong gagawin ng Pilipinas sa quantum computing? Like, what's
Oh,
the
Oh,
goal?
ayan.
we
Oo.
actually have uh, yeah, meron kaming balita, pero I don't think I can share it here.
Ah,
Uh,
okay. Okay.
Offline na lang tayo. Uh,
Okay.
Yeah.
yeah, so I think I'll just close this. So thank you very much, Jack, for
Salamat.
gracing us with your presence and with your expertise. I don't know how we can repay you, pero this video
That's very good. Mm.
will be there. A lot of people will get to know you more. Yeah. So and also thank you very much to the audience who are watching us. Yeah, so we would like to invite you to our group, One to Philippines. Um, so our group, we hold regular lectures on the basics of quantum computing. So, like for example, we will teach you how quantum computing is able to crack the RSA and elliptic curve encryption. We'll teach you how to do quantum searching via Grover's
Mm.
algorithm. And we'll also be teaching you on how quantum computing is applied in the industry. Yeah,
Mm.
so I think that's it. So once again, thank you very much, Jack, and thank you very much, guys, for attending. So
Mm.
yeah, that's it. Bye, guys.
Salamat Salamat, Jack.
Salamat,
Okay.
Jack. Thank you.
Salamat po. Okay.
Okay, bye.
Bye.